Well, he just ran it through the photocopier 7 times. I have 7 copies right here.
Conveniently leave it on the counter. That's tomorrow, right?
What?
What?
No.
Sunday.
Sunday?
Is that Game of Thrones?
Sunday. Sunday.
Okay, so last time, so let's review what we did last time. We started talking about derivatives, and we had this definition that is cumbersome, but gets the job done. Or we say we're going to take the limit as this thing gets really small. So what that allows us to do is discard any terms that are proportional to it, right? Get rid of them compared to other things. Anything without it is what we had left over. And so this is what we call our df dx. You will also see it as f prime, right? So it's f prime, df dx. It's easier to say. And we had started to make a list, right, of these things. So we had done a case of polynomials. We've been building up one at a time, and then we finally used the binomial theorem a bit. Some regards. What we said is if we have f of x is x to the p power, then df dx. So remember, this is, how does the function change as I change x, right? How does that vary with the variation of x? Okay. It's going to be then d x to the p minus 1. You go a long way with just that. And with using the fact that we saw that this is a linear operator, you can just write out the definition of it, and we say the derivative of a sum is the sum of the derivatives. So with these two pieces of information, we can write out the derivatives of any polynomials. Okay? So let's just remind ourselves, let's get a little bit of practice in. Let's think about, let's do something. Let's just do it without anything else. All right. Let's just do what we can here. Okay? All right. Let's just do it. So take a second, write it down for yourselves, and let's see if someone wants to volunteer and answer. So we'll take derivatives of all sorts of stuff. Rule here, so it's just these two things. So just take the derivative of each one individually. Okay. All right, we have some answers? All right, what do we get for the first term?
2x.
2x, good. What about this one?
Minus 1.
Good. What about this one?
Minus 4 over x to the 5th.
Good. All right, let's see about this last one. It's probably the only one that is slightly, it looks more complicated. It's all that's done here is, you think about this thing as being x to the minus 4. So its derivative is minus 4x to the minus 5. These are the ones that typically, years of teaching this, these are the ones that sometimes, you add instead of subtract. That's right. Good. Perfect. Now, there are all sorts of uses to this, and we may or may not get to those Friday. So I was debating whether to go about the uses of these kind of things or going on with our getting our compendium of types of derivatives that we have, which I think what we'll do. We started out with cosine last time and sine, right? But let's recall what this means is, in words, what the derivative is. Right? It itself, as you can see, it is a function. Okay. So the derivative is, or gives, slope of the tangent line to the function, so the slope to the function f of x at x, right? At any of those points. As a function of x, that's what it is. So maybe it's not so obvious what this kind of thing looks like, right? We could go through and try to plot it and figure out that this makes sense. But for simpler cases like x squared, we did last time, that's no problem. We can also do things like x cubed. So let's just quickly take a look at this. So x cubed versus x, it does something like this. And what's the derivative of x cubed? 3x squared, good. So f prime, 3x squared. Right. What does this thing look like? This is it is a polynomial. Parabola. Okay, so this would be the derivative, right? If I were to go and draw it here, so that would be x squared. It should be smooth. This is 3x squared. Okay. Well, does that make sense? Okay, in that the derivative is positive everywhere except for one point where it's 0, right? So if you were to sit there and draw, if you wanted to take, right, here's my tangent line, okay? It's really big and positive, right? And then it starts to, it's decreasing, 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 but it's still positive, decreasing, 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 still positive. It turns over just at 0, it hits 0, right? And then it increases and is positive again. That's exactly a parabola. So that makes sense. So what one can do, and what you will do, is you can start looking for certain points on your functions. There are certain special points, critical points, where function's derivative would change sign. Imagine we had an x cubed function like this, okay? Well, points here and here are special in that their derivative would be 0 each one of those points, right? So this is just a preview of what you'll do. Is it's called optimization. What's the maximum value of something in a certain interval? What's the minimum value? Well, I take a derivative set equals 0. I solve for x, and that would give me then, okay, where does this hit 0? Where does this hit 0? What about the next step? Okay, this is one derivative, and we write it df dx. We can take a derivative of the derivative. And the way this is written is, since there's two d's up top, 2dx squared is down below, it's written like that. Well, that is second derivative. There's nothing any more difficult about it, you just have to do it again. Okay. So then for this one, what's f double prime? That's the way I'd write this. So f double prime, what's the derivative of this? The 2 comes down 6x. So that's just this. Now, does this make sense? This says this is the slope of the tangent line to this curve. Okay? The tangent line here has a slope that is positive or negative? Negative. Remember, it's the value of the function. Here's, again, where you could get confused. The slope here is positive, but the value is negative. The value is negative, which means the slope here is negative. It turns over right at 0, and then the value becomes positive, which means the slope becomes positive. So this matches that. Again, we're going this way, and you'll be able to do the other way as well. And then this has an application in kinematics, which we talked about last time, taking the derivatives. It's not just x. Okay, x is just the thing that's being varied. Oftentimes in physics, we want t, we want to vary the time. What's happening with respect to time? Where is something when? And so its time derivative can give us the speed, or the acceleration. So let's then talk about some more functions whose derivative we can take. So now we have polynomials. Last time we motivated the derivative of cosine and sine, right? We started with sine. And what we found is we at least could justify, seemingly, that the derivative of sine of x cosine of x. Right? We at least showed it had all the same properties as cosine of x. we did this through graphical means. So here is sine. So it hits 0 at 0, and it's 0 again at pi and 2 pi. It reaches its maximum at what? Yeah, pi over 2, right? Pi over 2, it's 90 degrees. It reaches its minimum, 3 pi over 2. And its maximum is what?
1.
Yeah, it's as big as it can ever get, as small as it can ever get, -1. So the amplitude of this is just 1. Nope. We know what happens. What if this was 3 times sine x? What would happen to this?
The maximum would change to 3.
Yeah. Maximum would go up to 3 and the minimum would go down to -3. But where x hit 0, it would change. It would still hit those same points, right? And what we said is, with our yellow chalk, is the derivative, right? Yellow. The derivative hits 0 here, right? It's 0 there. It hits its peak right here. Now, what we've not shown is that its peak derivative is equal to 1. Right? We didn't show that. However, another sort of motivation. What is this? What is sine x when x is much, much less than 1? Has anyone ever done this on the calculator? Put your,
0.9999.
so put your calculator into radians. Do you have a calculator right now? Let's just put your calculator into radians and take the sine of 0.01. Sure it's in radians. What do you get?
0.009999.
Okay. What about sine of 0.001?
0.001.
Yeah, right. Still, that's not exact. There's a rounding error or sort of a precision issue with calculator. But what happens is, as x gets really small, sine x goes to x. Okay? They're higher terms, but they're very small. Because I'd be like, there's an x cubed term. That's much, much smaller. It's actually so small. What's the derivative of x? 1. Okay. Now, down here, it's -1, right? If you try this with sine really close to, your angle really close to pi, do pi plus 0.001, you're gonna get, you'll see that you get this minus, you get the minus x over there. So the derivative here is just gonna be -1. And then you're back up to 1 here. And what happens then is I have a derivative, which is periodic with period 2 pi. It has a maximum of 1, a minimum of -1. And it goes through 0 at pi over 2 and 3 pi over 2. We definitely know a function that does that. It's this. Cosine. So last time we talked about, are they perpendicular, or are they cross? You can check that. How you do that is you take then the derivative of cosine, right, and the derivative of sine, and you find out what those values are for the cross. You'll see whether that's perpendicular. What does it mean to be perpendicular? If I took 2 lines.
It's going to be 90 degrees every.
Are the slopes related?
I think it's the
Opposite of 2 and 1/2? Are they 2 and -2? Are they 2 and -1/2? What are they?
2 and negatives.
Okay. So we would need to check to make sure that we have perpendicular tangent lines at that point. Okay. So we have derivative of sine is cosine. Now the derivative of cosine, however, and I'll tell you another way of finding this too. So here's cosine. Okay. It hits 0 where? Where's the first 0 cosine past 0? What's that? How many degrees? 90, right? Which is what? Pi over 2. Then it hits it again. 3 pi over 2. It hits -1 at pi, back to 0. And then it comes back, wound back around to where you started. Right? Okay. Well, the derivative up here, obviously, is what? What's the slope of this line?
0.
Okay, so now we'll. This is 0. It's going to be 0 there. 0 there. Okay. It hits its maximum here. Okay, but it's negative. That's right. It's down here. It's a maximum here. Maximum is just amplitude, I mean, and it's positive. So it's going to be up here. And you can see, again, we have this notion of it's periodic with period 2 pi. Okay. It hits its max and mins at pi over 2 and 3 pi over 2. It's almost this curve right here, right? If I took this curve and just flipped it over, it would be that yellow curve, right? Which tells me that d by dx, or the derivative of cosine x with respect to x, is negative. Now, again, this is a little bit of, you know, again, I've said the word many times, but we're motivating these solutions. You can prove these, and a couple ways to prove them is you can go into here, and I can do sine of x plus delta x. Do you have anything that your mind automatically does when I see sine of something plus something? We know these kind of things. This kind of stuff.
Sine alpha plus sine beta.
You know these trig identities. Some and difference. There are some. One could use these kind of things. Okay. Another way of doing this is to use a series expansion for sine and cosine. You can write them out as a sum of different x to certain powers. Like here, we wrote down the first term in this series. The first term for cosine actually is 1, it turns out. You have a 1, has to be a constant, okay? The first term has to be a constant because its derivative is going to be 0, okay? So there are these infinite series you can write down for sine and cosine, and they're all just given in terms of x to the p. You can take the derivative, and what you see is when I take the derivative of the sine series, I get cosine. When I take the derivative of the cosine series, I get minus sine. So that's something that you go on in calculus, you'll learn a certain type of series, we call it a Taylor series. And that is another way to show that sine and cosine, these derivatives are that way. Another is to use the trig identities. Okay. But now we have another tool. So we have these things, right? So for sine x, we have cosine, and for cosine, the derivative is minus sine.
I have a question.
Yes?
What does a tangent line look
The tangent line.
like on a graph like this?
One of these? Okay, sure. So the tangent line would be given at a single point, right? So that one would be, well, this is a forward drawn. It should be just something that touches once. Okay. The line that would just touch, it just touches there. Okay. That's it. You say, well, it curves around and intersects again. No, that's true. But it's just here, right? Just at this point, right? There's no overlap and it doesn't intersect this way or that. So my tangent line is like this, it's like this, right? It's like this. And then on this side, we have here, here, here. And we flip over, we got this kind of stuff going on.
So, tangent doesn't have a whole series, just like sine and cosine?
Oh, are you talking about the different things? The tangent function?
Yes.
Yeah, we're going to get to that almost immediately here. Because I want to talk about how does one go about taking derivatives of a product of functions. So going forward, just to let you know the kind of things that I'd like to get through this week is one to do derivatives of polynomials, we've got that. Derivative of the sum of functions, sines and cosines. We also want to talk about these two. Okay. This one is a nice one. It's the most nice because its derivative is itself. So that's yeah. Yeah, its derivative is itself, which is really nice. That's sort of the, this thing does this, right? It looks like this. And that's what its tangent line is too. Right? Everywhere it has the same derivative. That's what's special about this thing. So whenever you start to talk about systems that change with respect to time or with respect to space, some of these things will change proportional to themselves, or they'll decay, let's say, proportional to themselves, for an exponential decay of radioactive things. Okay, well, we'll deal with that as well as we talk about the exponential function. So these are two that I want to get to. And the others are, how do you do this? How do you take the derivative of a product? And then how do you take the derivative of a composite function? Right. We'll do this one to get at these a little bit. One way to do it. And this one we'll do, you can motivate this graphically. Okay. So the top one, since it's a product of functions, you'll hear it called the product rule. But it's a simple one too. So what we have here then is the following. So imagine I have something like this. Some kind of square. So this is a product, right? We have some length and some width to our I don't know if anyone do it, but do width, maybe it's not an omega, and a length. And what all this is, we want to know about a little variation. That's all we're doing here. Right? We've been looking at a single function. How does it vary with x? So I'd like to know, how does this product change with some variation? Okay. So I can vary these things just a little bit, right? Get a little bit of variation in L, little delta L, or if it's really tiny, say infinitesimal, then it's a little dl. And then I can also have a little variation in the width. And so this would be all how all this area changes. So what we'd like to know then is this kind of product. How does this thing change? So there's some parameter, there's something that underlying that I'm varying. So make sure it's properly done. All right. Well, the change in this, right? The change in this is just this shaded area. So graphically, we just have our shaded area. And this little bit with the crosshatch in it, where this goes this way, and well, you could have two of these here. This thing is very, very tiny. So those DLs and DWs we take to be go to 0, but their product is negligible compared to just one of them. So this is like thinking about x and x squared, where x is very, very small. You can neglect x squared term compared to x. So the change, what we're asking for here, is just graphically what's the change in this. So we get this delta L, right, times the width. That's that piece. Okay. So if you think about it without the x, it would just be dl times w. So there's some underlying parameter that I'm varying, and as I vary it, the length of this changes and the width of it changes. So this is just reading off rectangular areas, right? This is a width, and that's dl, so that's the area. And what about this piece? What's its, length times width? What's the length? Length. That's all, is it? Right? It's L. And then what's its width? dw. And again, there'd be, so this is a variation with x. We varied this, it could be time, it could be space, it could be whatever. Right? And now you argue, wait, what about this piece up there? Well, that's dl times dw. Okay. And in the end, we're taking these things to be incredibly tiny, so we just keep these two terms here, right? So that's negligible compared to these. So again, this is just a motivation for one can also, I keep saying this, but the definition of derivative, you can go through and write down f times g, and you add x plus delta x, and there's little techniques you can go through. It's not that enlightening, but this is, I think, a good explanation, this nice graphical way of grabbing a hold of this concept. So what you do then is you hold one of them the same and you vary the other, and you add to that the variation of the other, well, you hold the first one the same, okay? So this is what we call the product rule, and what we have then is this. There's a great question, was not planted, what's the derivative of tangent? We're gonna do that next. So what this would be is df dx times g, right? Derivative of the first one times the second, plus the first one times the derivative of the second, okay? So you have this operator dx, and it goes through and bang, it hits the first one, doesn't touch the second. And then it goes through and hits this one, and the first one comes along, right? But again, this kind of picture graphically shows what's happening there. So we're looking at these infinitesimal changes. So if you think about, just taking a step back, think about your average speed, right? You have these non-infinitesimal, these large changes in x and t. What you do is you take those changes to be smaller and smaller and smaller, so this is a change over some, non-zero, big interval delta x and some interval delta t, but then you start to squeeze those intervals down. And this tells you at a single instant what your speed is, the instantaneous speed. Right? We throw a vector on that, it's instantaneous velocity. So we have this sort of average of things, but then we squeeze these things down, so we're taking this limit as they're going very, very small, right? And then that's the same thing here. Okay, so we're taking these little bitty limits. So in our shaded area, we're just squeezing these things down, so as this thing goes to zero, it goes away compared to those. So just, okay, so what can we do with this? The first one is we can answer the question that was just asked, which is, what's the derivative of the tangent? So now, like a lot of things in math and physics, we have these building blocks on top of each other, right? We have a few rules, and now we can put them together to discover new stuff. So what then is a derivative of tan x? And why in the world would I write that down after telling you about the product rule? Okay. Tan x is just tan x, right? But it's not. What is tangent? It's the what? Sine over cosine. So that's a product. Right? That is a product. That's a product of sine x times so reading off from here, I get df dx. This is my f, it's like f. And then this is g. Okay. So derivative of sine, cosine. Okay. And then we don't touch the g. So we just have a 1 over cosine coming along. And then we add in f times derivative of that.
Where
Right.
did the inverse come from?
Because tan is. Right?
Yes.
Now, a point to make is these are different. That is not the inverse cosine. That is 1 over the cosine. This is 1 over the cosine. The other one is, you see cosine minus 1 here? That's not 1 over the cosine, okay? That's the inverse cosine. So cosine with the minus 1 before the x, or you'll see it's called arc cosine, okay? That is actually the inverse trig relation, not 1 over the trig relation, okay? So this just came from the fact that I have 1 over cosine.
Yes.
Now, we're almost there, but we actually don't know how to take yes.
Can you tell me how you got from up there to cosine over cosine?
Yeah. Derivative of f with respect to x, derivative of sine is cosine,
Right.
times, what's g? 1 over cosine.
Okay.
Yep. Yeah. Yeah, let me know. I'm trying not to do any sleight of hand here. Okay. Yeah, cosine x times 1 over cosine x. And now we run into another roadblock. What is the derivative of 1 over? Right? You might say, well, I know how to do x to the minus 1, right? It's minus 1 over x squared. But this isn't x to the minus 1, it's cosine to the minus 1. So I'm not sure if there might be something else there. Okay.
Change it.
What's that?
Or it's cosecant.
And so it's going to be something different. In order to get to that, okay, we have to do this. I'm trying to show you there's some things you might want to do here, and you got to, okay, I hit a roadblock, we need to go back and figure out how to get there from here, okay? So I could have started with that, because I know the order of how things go, right? That smooths everything out. Sometimes it's nice to see, oh, okay, I have this new rule, let me try to use it. Maybe the first place I'd think about using it would be this. You might think something like 3x squared, which is also fine. But that's probably like a 3x squared. We can do that. That's trivial. I want to try something a little bit more adventurous here. But we run into a roadblock, right? So we actually have to take another step back, and we got to figure out what on earth this is. What does it even mean? Let me try to gather what we've done so far. So we start to build up this library of stuff and get rid of our definition of the derivative. So some things that we have. You can put parentheses around these. Okay. And then we also have product rule, which so far has been a bit of a bust. It hasn't helped us do the one thing that we were wanting to do. All right, so we got one more. Composite function. Why on earth would my mind even go to a composite function when I see this? Again, what it is it looks like, right? It looks like 1 over x. So what if I said I had right, f of x is 1 over x, or that f of g is 1 over g. Okay, so these look kind of similar, right? But now this itself is a function, okay? And that's what I have here. I have 1 over cosine. So this, what I'd say is f of g of x, where f of g is 1 over g, and g of x, cosine of x. Have these nested things. And we could continue on, but this is as much as we do, is just be one inside the other, right? So f of g, what you do is, where I see the g, I take this and put it in there, right? And then this is just a rule telling me, you feed something into f, it's going to do that to it. Sometimes I can just feed it x, but sometimes, like this is g equals x, sometimes I can feed it a different function. I can feed it something horribly complicated. Right? So we need to know then, if I can take the derivative of f of g, then I can do it for the case here, we're done. We have our problem solved. So let's then think about what f of g of x doing. This is the thing that we want. So f depends on g. So here's the motivation for it is, I'm trying to change things with respect to x. Okay? So you can almost think of it as gears, or you can think of it as links in a chain. Right? You may have even heard the name. The chain rule is what this is called, because we do a chain of operations one after the other. But if I vary x, what happens then? So g of x will change. Right? We call that dg dx. Right? I'm varying x. Right? You have some x. So I'm varying x, and as I vary x, g changes. Okay? If g is changing, then f is changing. That That makes sense? Just think about our example here. If we have f of g is 1 over g, and g is cosine, if I change x, then g changes, its value changes. If I change g, then f changes. So you can think about these as gears, right? We'll draw all the teeth for you, but something like this, right? I have these kind of interlocking things, right? And this way. And as I spin g, okay? As I spin g, then I'm going to spin f, one after the other, right? I rotate g, and so f is going to rotate around as well, okay? We can think about do our teeth, our tooth, gears here, but they do something like this, right? As we go through. Okay. So they have different number of teeth. They might be able to interlock somehow. If we make them the same, then they'll actually catch up a little bit. Sorry, I'm trying to obsess over my bad drawings. So if I change G, then F would, right? I'm turning the crank on G. Okay, what's going to happen is F. So the crank is I'm changing X, right? Got this. Let's see what, got a handle. I crank it, okay? My crank, that's my X. I'm changing X, G is going to move, F's going to move. Okay? And they move one after the other, right? So you end up then by saying, what's going to happen as I vary this whole thing, right, is I can change F, okay? So F will have a change with respect to G, right? As G changes, F changes. But then also, okay, as I change X, G is going to change. So you can think about this going almost inside and out here. I start in the inside, and I see how it changes, okay? Or you can go outside in. I change the whole thing, F, the big thing, okay? So as I alter G, F changes. But then as I alter X, right, G changes. So this is this chain. It's one after the other, right? Going out to in. So overall then, what I'd say is you want to identify, and again, in practice, this looks a lot worse whenever you're just explaining the general principle of it than when you actually get to it in practice. Okay? And like most things, it's actual going through problems. You get quickly over the learning curve on this one, and it can be no problem for you. So here's what I'd say then in this case, right? Let's do this here. So we can formally identify, for the case of cosine x to the minus 1, we identify this way, right? So to take the derivative of this, we say f is 1 over g, where g is cosine. So what will we get? Okay. Again, we're going from the outside, so we take the derivative of f with respect to g. Okay? So what do I get? This is g to the minus 1.
Right, so it's negative g.
So the minus 1, right? We're using this. So minus 1, right? Minus 1, g to the no,
Negative 2.
negative 2, right? We subtract, okay? So p x to the p minus 1, p minus 1, minus 1, minus 1, minus 2, okay? So minus 1, that's g to the minus 2. Right? So we're working this way, and now I go inside, right? I'm working through this chain of procedures. And I just take the derivative of g. G is just cosine. What's the derivative of cosine? Negative sign. Now we can put it all back together. Minus minus is a plus. Right? And then g squared is, g is just cosine, so it's cosine squared. So cosine squared, right? So what we'll do on Friday, and when is your lab? It's tomorrow. Okay. Didn't know when you might do the recitation. We'll do some examples of this on Friday, some more of these. So let's finish this one out. But these are crucial. They're things you use all the time. These two rules. And I'll sum them up again here in a second. But let's finish our problem. And so we have then this is derivative of tan, we get a 1, that's cosine over cosine. And now what do I have? I have sine times sine, right? Sine squared, cosine squared. Okay. That's the answer. That's the derivative of tangent. And we can make it look nicer, and we can combine these things, right? How would I combine them? How would I add these things up? We're just adding fractions, right? One of the fractions denominator is cosine squared, the other one's denominator is what? 1. So I'd write this one, I'd write 1, it's cosine squared over cosine squared. Okay. And I have sine squared. What's the numerator?
Could be 1.
1. So we get 1 over cos squared x, and it has a name. 1 over cosine is secant. Okay? I literally don't have tan and cotan memorized at all. It's just, you can do it in a snap. Okay? It doesn't take much time to go through and do it. So the derivative of tangent is 1 over cosine squared. Yes, question?
I'm just curious how we got this extra minus sine x.
This? Okay, so that came from df/dg, that piece, dg dx is that. So you've taken the derivative of the overall form, and now you go in and do the specific case, right? So we have the overall derivative of f, right, df/dg, g is 1 over g. Okay. The derivative of g to the minus 1 is minus g to the minus 2. But then we have to multiply by the derivative of g itself. So these are the Frankenstein gears that I drew for you. You shouldn't have done that. Practice homework. So right, we have to do this.
Why did that appear?
Why did this appear? So this is just the rule for doing the composite function. Because what it is I'm varying x, so g changes. And when g changes, f changes. So it's this chain of processes. I change x, g changes. If g changes, f changes. You could put another one out here, h of f of g.
Right.
And I have dg dx, df dg, dh df. And it's just this chain of gears turning.
Where did that appear?
Ah, good question. Okay, so this is derivative of cosine minus 1. Okay? That was this. I was not even clear about that. Taking the derivative of cosine to the minus 1. So we said this looks like x to the minus 1. But instead of x, right, it's cosine. So it looks something like this, 1 over g, but g is cosine. So f of g is 1 over cosine. So where this came in is we were doing the product of the derivative of f, which is sine. Derivative of sine is cosine. And then cosine x to the minus 1, that comes downstairs. And then plus f times the derivative of this. So that's why we needed that.
Okay.
Then we had to go back and talk about this new rule just in order to get at this thing.
So the only reason we applied it like that is because it has a negative sign?
Yeah. If it was just cosine, we know the derivative of cosine.
Right.
But cosine to the negative 1 is something different.
Right. So you're saying because it has a negative, we have to apply it like this?
Yeah, because this is a function of cosine. It might not seem that at first because it's just 1 over cosine. This is a function of cosine, right? And that's cosine to the minus 1. So we can do other things, which we'll do. A simple case, I'll leave you with. Is this clear? We're good? We're going to go through a lot of examples of this Friday because I want to really nail this stuff down. These are the two big things. So being able to do this, and then so the product, and then doing these composite functions, doing a chain of operations. So let's take a look at another way one can do this. So you could have something like cosine raised to whatever power, right? So some examples where you need the chain rule. cosine to some power, okay? Or let's do it this way, so b is not minus 1. Sine to some power, right? This looks like this case. It looks like x to some power, right? How about something like this? Cosine of some function, g of x, right? So this is a function of cosine. This is cosine of a function. Usually what we need is things like this. What about cosine of 3x? Right? So, well, what's the derivative of that? Well, it's going to be minus sine of something. How do I deal with the fact there's a 3 in there? Okay. So these are the kind of situations where we'll need this chain rule. We'll go through and do examples of these next time. So again, we're going to work on this out to n. What we have is overall my function looks like cosine of something. So the derivative would be minus sine of that something. But then I have to take the derivative inside of there. Because as I vary x, g changes. As g changes, this whole thing changes. So I take the derivative, I do all of this, and then I go in to there, take its derivative as well. And of course we can do sums of these things, right? Because we know how to deal with them. You can then do products of them. You can do all sorts of stuff, right? Now we can take huge amounts of derivatives, all these different combinations of things. So what we'll do on Friday is we're going to go through, because it takes a little bit of working through to get, comfortable and familiar with this piece, I think. That's my experience where things can be, to actually identify what's what in here, right? Because that's what we were having. Why would we even think of doing that with cosine of minus 1? Because it looks like it's just a cosine thing, but it's a function of cosine. So it's good to be thinking about things that are functions of these, right? Cosine sines, e's, natural logs, any of these things. We'll have to use this chain. Yeah.
So this makes sense, but why couldn't you just put the exponent in front and then
What would happen?
change it to a negative 2?
Right, what would happen? We would get minus 1 over cosine squared, right? But you haven't taken into account the fact that x has changed. So you missed the sign. Because what we got is the derivative of this was minus 1 over cos squared. And we had to multiply by the derivative of cosine itself. Minus. So that cancels. You missed the sign. The sign function. Right. But no, that's correct. That's the first thing one would try. You say, it looks, but you're on the right track because you're thinking, oh, it is just like a 1 over x. So why is it not minus 1 over x squared? Because it's a function of x. It's not x itself. Right.
It's like there's something in the parentheses.
Yeah. Right. This thing inside of here makes this thing change, which makes this thing change. And so we have to go this way. So I think. Right. So we'll go through more of this on Friday. Work some example problems. So we pretty much have all the tools to do all sorts of derivatives now. Yeah. And of course, once you have that, you can do all sorts of physics. Once you have the technique of being able to take derivatives, we can do things like find maximum and minimum values. We can actually look at how these things change with time. We can solve differential equations. Because in physics, we want to know about dynamics of objects. How do they change with time? We'd like to be able to solve for those quantities. We'd like to be able to describe them. And derivatives are a language for that. And of course, we can do the other way.